Alright, I want to look at linear approximation, and on the calculator here I have the graph of y equals the square root of x. And this is a differentiable function if x is greater than 0. It's smooth. Remember, that means that differentiable at a point means that the derivative from either side would approach the same value. So what I'm going to do here is I'm going to pick the point where x equals 2. The y value would be root 2, and I'm going to zoom in on the graph near x equals 2. There's about x equals 2, zooming in, enter, and the graph goes in. Okay, I'm going to get a little closer. I'm still at x equals 2, so I'm going to zoom in again, and I get even closer. And I could keep doing this. What you're noticing, though, is that the further I zoom in on the point, the closer the graph looks to being a straight line at that point. Okay, and this is the idea of linear approximation. Let me just do it one more time. At x equals 2, I'm going to zoom in even further. It appears that the graph is a straight line at this point, and that's the idea of linear approximation. If you are really close, zoomed in at x equals 2, then a line at this point, a tangent line at x equals 2, would approximate the graph at that point. And this is what we mean when we say that a differentiable function at a point is locally linear. If we zoom in at the point where it's differentiable, then the graph will eventually look like a straight line. And because of that, the tangent line at that point will approximate the graph at that point. So what I'm going to do is I'm going to use the blue line as an approximation for my function at the point x equals a. And we can of course get the equation of a tangent line. We know how to do that. If I make this point a comma f of a, I can use my point slope formula, which is y minus y naught equals slope x minus x naught. And I'm going to bring my y naught over to this side. That would mean that my tangent line would be y equals, we're doing the tangent line at x equals a, is f of a plus, the slope would be the derivative at that point, f prime of a, x minus a. And so what we're going to do is we're going to use the tangent line to approximate the curve at that point. So f of x, which is our curve, okay, we had f of x here, which was root x, but just in general, no matter what my curve is, my curve f of x is approximately the tangent line at values of x close to a. And we're just going to take this one step further. We're going to do a substitution here. We're going to say, let's let delta x, the change in x, be this piece right here, x minus a. So therefore f of x is approximately f of a, my starting point, plus my change times the number of units of that change. The further away that we get from x equals a, the greater the difference between the value of the function and the value of the tangent line, and that's called our error. So the way we measure our error, e of x, let's call it, is the change in the actual function from the tangent line. The absolute value of that, because we can make an error in either direction. Alright, let's use this concept to approximate, to do the linear approximation of root x at x equals 4, which remember means that we're going to use the tangent line at x equals 4 as being close to the graph at points around 4, which you can see. The blue and the red are almost the same thing. So f of x is approximated by the equation of the tangent line, which would be f of 4 plus the slope at 4, which is f prime of 4, times the change in x, or x minus 4. Squeeze it in there. So let's calculate this out. F of x equals f of 4, which is the square root of 4. That's the y value of my starting point, plus the derivative at 4. Well, we know that f prime of x is 1 over 2 root x. So this would be 1 over 2 root 4 multiplied by my delta x, which is x minus 4. It depends how far away from x I'm at. And if I simplify that, my approximation will be 2 plus a quarter of x minus 4. Alright, so let's use what we've just come up with to approximate the square root of 4.1. So my x value is 4.1, so I'm plugging that in. This is the square root of 4.1 is approximately 2 plus a quarter of 4.1 minus 4, which is 0.1. That's really delta x. And if I work that out, that's 1/40th, and as a decimal, 2.025. Okay, that's my approximation for the square root of 4.1. If I just bring back the graph just to recall how this all relates, I have my tangent line at x equals 4, and I've used it to approximate 4.1. Let's just put it there so I can see it. That's really the y value on the tangent line. This is my approximation. My actual value of 4.1 is the y value on the graph, on the square root graph. This is the actual. So I can see that the actual value of square root of 4.1 is a little bit less than the approximation. But if you go to your calculator and type it in to see how the two actually compare, they are pretty close to one another. And this approximation is close to the actual value. Keeping in mind, goes on endlessly. This is an approximation too. But the approximations are close because the change in x was small. Delta x was only 0.1. By the way, if you want to just extend this to the discussion of the error, which we mentioned earlier, the error is the absolute value between the function and the tangent line. So the error at 4.1 is f of 4.1 minus the value on the tangent line, which is 2.025. And so this value minus my approximation gives me a negative value, but the absolute value of that is my absolute error. So 1.5 times 10 to the negative fourth. Pretty darn good.